So I think I'll have one of the TAs lead the homework portion of the recitation. I'll jump in when needed. Kyle, would you mind doing that this first time?
Sure, hold, give me a moment. Okay. Let me pull up the homework problems, just ready to go. Okay, and I got those pulled up now. All right. So how's the homework going for everybody in general? Can you hear me?
Yeah, we can hear you. For me personally, it's been going pretty well. I guess the big thing is I just got into the algorithm problems and just kind of trying to figure out exactly what's being asked for me to do. And then in problem 5 especially, I'm not sure about this condition number. I haven't looked into it too much, but wondering if there's maybe some help we could get there.
Okay. So are you on the second set of problems?
Yes, on the problem of approximation 1.
Okay. All right. So sorry, there was some noise in the background of one of the other people. So what was the first question? I didn't quite catch it. So
Yeah, so with problem 4, we're supposed to create an algorithm. So by that, to create some kind of code. And in the example in the notes, it goes through and uses a bunch of functions that it said was referenced in previous ones. I'm wondering how in depth do we need to create functions for this algorithm? Because right now I kind of have just a MATLAB code that you put in what bases you want and such.
So number 4, remember it's orthogonal projection in Rn. So you're just doing dot products. So you don't need hardly anything in the algorithm above is for integral-based inner products.
Okay.
So the point here is that you should look at that code and basically I want you to understand, the point is if you understand the idea, you should be able to look at that code and know what to strip out and not need, because it's just basically a bunch of dot products.
Okay, cool. Then that makes sense. And then with problem 5, kind of because it's tied to problem 4, we have this computing a condition number. Is that Wikipedia, do you think that's a sufficient source to figure out what a condition number is? Oh wait, I do remember that a little bit. Never mind. Okay.
Yeah, I mean a condition number.
Back in linear algebra.
Yeah, you don't really need to know very much about it. I'm going to talk a lot about it later, but right now you just compute it. And all you have to know is big numbers are bad. That's the extent of your knowledge at this point. And so what you should see is that as you get closer and closer to a numerical linear dependency, the condition number should get bigger and bigger.
Okay. And then just a clarification question on 5. We have this epsilon, which is within one-dimensional real numbers. Is that correct? Am I reading that right?
Yeah, so you're going to take like, you're just going to like create some, what I would probably do is you just create a bunch of vectors and maybe you pick 3 of them or 4 of them, but pick 2 of them and basically make them the same vector, except for one of them is like epsilon plus the component number, like the number. So let me, so like, let's see.
So
you really
like if
can do
you,
this any way you want.
like if you took problem 2 and replaced the 3-dimensional or the E2, replaced the second component with epsilon.
Exactly. So let me, so this guy here was set to epsilon. Notice as epsilon goes to 0, it becomes E1. And that would be a linear dependency because they're the same vector. And so as you let epsilon progressively get smaller, the condition number should get bigger. And what you
Okay,
should
so
see, what you should see in your matrix is that you'll end up with columns that become more and more linearly. In this case, you'll have a column, 2 columns that are becoming the same column.
so we're supposed to repeat problem 2, not problem 4.
I kind of left it up to you.
Oh, okay.
In 4, you can do whatever you want. You can pick any n value that you want.
Okay.
Yeah, one thing that I would say is like each of these problems is just kind of building on the previous problem. Like 4 is just a generalization of the first problems. It's not yeah. So I mean you're exactly right that you can do 2, but that is essentially doing the same thing as doing it for 4.
Okay, that sounds great. Thank you.
All right. How are things going for the other students, or how's things going for everybody else?
Just a clarification, Kyle. UH and VH, those are just abstract. They're not supposed to be like a specific vectors in R2 or R3 or Rn or Rm.
Sorry, your audio is really, really bad, at least on my end. So
That all week. Let me repeat the question. So for part 1, for example, UH and F are just abstract vectors in R2 and R3 respectively, and then throughout the rest of the exercises as well.
Yeah, I believe you're asking, is everything, are they just all vectors in some Rn?
Yes.
Yeah.
Okay, thank you.
Yeah, there's no integral quantities yet because I haven't actually shown you any bases. So that comes next.
A quick question on notation. The bolded RN in number 4 and the non-bolded ones in the other places, are they just the same?
Oh, I'm glad you brought that to my attention. That's actually a typo.
Okay. Thank you.
Yep. Oh, thank you. That was a good catch. It needs to be fixed. Let's see. Let's see. Yeah.
Anybody else? Did we get everybody's questions answered?
If no one else is asking questions, I just didn't want to dominate the question because I really don't even know where to get started with this. The like the first question, I'm not sure, like, am I just supposed to arbitrarily pick vectors and find them, or are there certain numbers we're supposed to be using?
I describe, so we're talking about this problem right here, right?
like you said, they all kind of build on each other. And so it's kind of like, well, starting with number one, I don't even know what those vectors need to be.
Right there. That's the description.
And so they all are exactly the same. They have 1 in position I.
Well, E1 is 1, 0, 0. E2 is 0, 1, 0. Remember, it's on position I. E3.
Okay, so you're defining I as E, that's E sub I right
that's
there.
Subscript.
Okay. So how does F relate to Rn? I'm still having a hard time with this notation, and it, I don't know. So R to the N, let V be, when you have this set equals, is this defining V as being R in the cubic domain?
Yeah.
Are you asking about this guy right here?
Yeah.
Sorry, Kyle. I keep jumping in. I asked you to help out, and then I.
So do you want to handle this, or do you want? I can handle this if you want me to.
Maybe this case, maybe this time, I should do it since these are problems that I just wrote. So,
All right.
but going forward, I would like one of the TAs to start the recitation period. Okay, so Eric, is your question, what is R3?
So if I'm understanding it right, R3 is saying that it's in the reals domain and it has like a 3x3 matrix.
It's this this whole space, XYZ, this classic space that you've used for many years, that's
Right.
called R3.
Right. So you have
3 dimensions.
So
yeah.
it would not be a 3x3 matrix, but a 3x1. Like just
if you're defining a point, it'd be a 3x1.
Right.
Yeah, so if you have a point right here and you want to know what its value is, it's going to be X, Y, Z, right?
Yeah. So when you say V and then that sign, the colon equals, is this setting it equal to? Or
It's actually a little
defining
bit
V?
different. The colon equals means is defined to be.
Okay.
Defined to be. It means let's just define V to be R3 and VH is defined to be R2.
Okay. So is VH a subspace of V? Is it like one of the planes?
Yeah, so R2 would be like this plane here.
Right. It'd be the XY, one of the XY planes.
Yep.
We're not necessarily defining at this point what XY plane it is. We're just saying it's an XY plane.
Yep. Well, I just am assuming it is the XY plane. You set the Z coordinate to 0. You get the
Okay. Okay. And then you're setting F. So F is, are you setting that as a function or is it just a constant with those values E1, E2, and E3?
That's what F is.
Right.
It's 1, 1, 1. Because E1, right, is 1, 0, 0. E2, 0, 1, 0. Add those 3 vectors together, you get 1, 1, 1.
Yes. Okay.
Basically, this problem is you're going to be projecting this point onto the plane here. Draw that a little cleaner. All right, so we have X, Y, Z. This vector here is E1. This vector here is E2. This vector here is E3. So that should help you see why they're a basis. And then I give you a vector F, which is like up here somewhere. F 1, 1, 1. So you should see that, right? The shadow of this point on the XY plane. Right, I didn't quite catch that. This is what UH will end up being, by the way, when you run this problem.
Mm-hmm. So you're defining UH to be within the R2 space. And then when you say find the best approximation UH within R2 to F, when you say 2, that's meaning project.
You're just trying to approximate F. So UH is going to be an approximation to F. And you're looking for the solution UH in the subspace VH. Whereas F lives in V.
Right.
F does not live in UH in VH.
Okay. That makes more sense. Thank you.
So I don't believe that there's no other questions, by the way, especially since a number of you, right, remember correctly, haven't turned in the first homework. Be brave, guys.
We're allowed to ask questions for the first homework too?
Of course.
Dr. Scott, I had one quick question. You have in your to-do at the bottom of both of the notes to create a key for homework problems. Is that something that is that something you're going to put out and we'll be able to kind of redo homework that we didn't do right and turn it in again?
Can.
Okay, that would be really helpful.
Yeah.
I mean, I have a quick question on formatting. So like last homework, I typed it all up in LaTeX and turned in like a PDF. But it sounds like for this one, there's some coding we need to do. Like, is it MATLAB, Python? Like, does it really matter?
Doesn't matter to me.
Okay.
Yep.
The one comment that I would make about MATLAB or Python is that you may get a different TA who is willing to help you depending on which one you pick.
What about Mathematica?
I'll say I'm willing to try, but I may have more trouble with Mathematica.
I'm much more familiar with like Julia and MATLAB. I've done very, very little with Python, so.
Yeah, and I did this when I did this class, I did it all in Python, and I still use it. So,
yeah.
So I think that the TAs will be able to help you with either. I can do MATLAB, I just don't like it.
Sad day.
Chris, we can't be friends anymore.
Greg, we've already had this conversation.
It's all right. Greg and I can't be friends anymore.
Okay, well, I'm happy to open it up now to the wider group for questions on any topic related to what we're discussing, high level, low level.
So I actually do have just a quick question on homework one from number 4. I posted it on the, so it's asking us to plot the analytical error. So the integral just gives us a value, right? So are we supposed to?
Okay, we're going back to.
Yes, this is set 1.
Okay, let me
4.
Give me a minute to catch up here.
That problem was adjusted a little bit, so I'm not sure if you went back and saw it.
I did it before it was adjusted, and I did it again since it had been. So I mean, just plotting the analytic integration area. I mean, so the plot of an integral, I mean, the integral is just a value, correct?
Yeah. So you get a value for every value of xc.
Okay. Okay, so I'll just take, you know, some arbitrary xc and say, okay,
so you've got like some, right, xc, what do I do? It's from 0 to 1, right? So 0 to 1. This is going to be f of xc. So what I'm saying is chop up your domain into a bunch of little so maybe this is xc, 2xc, 3xc, you know what I mean?
mm-hmm.
And that's what goes into the limits of integration. So you'll compute a number at every single one of these values, and then you'll plot all those numbers.
Okay, so 0 to xc to 2xc, 2xc to 3xc, and so on.
Yep.
And then the same for the, okay, that makes more sense.
Well, it'll be 0 to xc, 0 to 2xc, 0 to 3xc.
Oh, okay.
Like this, for example, if we're at some arbitrary n, maybe I'll even call it delta xc. You pick some increment, right? All of these are delta xc, right? The difference between the value that you plot at that point is going to be 0 to n delta xc of the integrand.
And I'll just carry through to the other ones as well. Okay, that makes more sense.
Basically, what you're doing is you're plotting the area under the curve as you go, which is a measure of the error between the exact guy and the approximate guy.
Yeah, I remember you drawing that last year. I just couldn't figure out how to actually plot, how I would go about plotting that. That makes sense. That makes sense.
I'm curious for the BYU students, does this seem like a mathematical course to you?
Absolutely.
At the start, yeah.
For right now, it does, yes.
Okay.
So I don't want to take up the time that is supposed to be for your students, but if there's no more questions from them, I do have a bunch of questions on number 4 that you're looking at right here.
Sure. I'm sure there's more that are not speaking up, so happy to.
So if we look at the equation E tilde sum n of C, you're defining it as your function of sine of x, and you're taking the integrand of that, which you just kind of explained down below. And then you're subtracting out to get kind of an error value from between that being what we're calling probably our true answer for now. And then we're looking at this approximation answer using sine h, ci, wi. When I'm writing up this equation, I want to write it up for wi, and I go back to the documentation. I look up the definition for wi, and it's defined in terms of c sub I squared, and then also the Legendre polynomial Pn of c. And when I try to build those equations for wi and the Legendre polynomial using the definitions in there, I cannot get them to come out to what I would expect for a Legendre polynomial.
You just want to use these points. You don't have to, you just use these points. They're already figured out. You don't have to. They're just written. They're just like a table. You just look them up and use them.
So when it says the how does it say it? Let's see, the 0.
So let's do a three-point quadrature, just to make sure we're on the same page. And you have some integral, let's say f of x dx that you want to approximate, right? So what we're going to do is we're going to go 1 to 3 of f of Maybe we'll do exceed here since that's what we did before.
Maybe put your limits of integration there too.
I'm going to do, so in this case, it's going to be f of -1 root 3, or no, sorry, what is it? That's not right.
So, Dr. Scott, I think you're skipping an important step.
Okay.
You need to map the integral back to -1 to 1.
Okay, I didn't want to let's just do this for now. Let's assume that it's -1 to 1, okay? This is kind of what we call standard form, -1 to 1. It's going to be 5/9 plus, see, I'm just picking the numbers right up here. F at 0 times 8/9 plus f at root 3 over 5 times 5/9. So when I say use a n-point quadrature rule, in this case a 3-point quadrature rule, this is exactly what I mean. You just go and you look the numbers up, evaluate the function at the 3 points, and multiply by the weights, and that becomes your approximation to the integral.
Okay.
And then in this case, what we do is the limits of integration that you're interested in are actually from 0 to c. So you just have to do a change of coordinates between -1 to 1 and 0 to c. So. And that's it.
Okay, that's a lot simpler than I was trying to make it.
Yeah, if you're trying to compute the zeros of Legendre polynomials, that
Yeah,
is complicated.
that's what I was trying to do. And the equations weren't coming out right for me. And I have canned equations for those built into Mathematica, but I was trying to get the equations to work here. And I was like, no, it wasn't working for me.
Normally with quadrature rules, somebody derives all the points and puts them in a table and publishes it, and then everybody else just uses the tables.
Okay.
So also another question about, so we have the sine h xc. So we have sine xc is approximately sine h xc is equal to that truncated Taylor series. When we're going to those integration errors, every time we see the sine h, do we plug in what that truncated Taylor series is? It's like for this first, the analytic, we have sine x minus, we would have then x minus x cubed over
E of c x that's the integral.
Okay. And then so the same for the approximate, we have the integral from sine x minus, and then so we have the sine h xc1. So when we do our change of variables, we'll plug in our new change of variable equation into each of those x's.
Everywhere you see x, it'll become x of some other variable.
Okay, that's what I thought. Just clarify.
Okay. Anything else?
So, on this question number 4, I ran my code for it and came up with some weird graphs, and I was wondering what type of graph to expect.
Well, they should be smooth, pretty smooth looking. So does anybody have these graphs that they could share?
I have mine, but
Well, you can share it. I'll enable, take a look at it. Let's see here. So you can go ahead and share it now.
it's still disabled.
Maybe
I
can you
just-
stop sharing first, Mike?
Yeah, good idea.
still doesn't work.
Allow participants to, okay, go for it now.
Awesome. So here's what I got.
Let's see, sine. The first graph, I can't tell.
They're on top of each other.
Well, there should be an error. It should be the error, right?
So I have errors as well, but it was so weird that I had to put this guy up.
I mean, that's not the error. That's just plotting the functions. I would expect them to be close to each other, but the error, you know, it's going to be in the trailing digits, but it's going to be something.
Right. So this is the error with.
That looks better. Except the error. What is the scale of the y-axis?
It is 1-to-1. It's exactly the same as here.
So you're saying you have an error of 0.4 at c equal to like 0.7.
That's for n equals 1, right?
Oh yeah.
Yeah.
Okay. Let's see what n equals. Okay, what does n equal 2 look like? In other words, the error should be getting smaller, right, as you go. See,
here's a combination of the pictures so we can see them. There's N1, N2, N3. And I think N3 and N2 are on top of each other. They're this purple one. Then N1 is this one.
So N1 is more accurate than N3. That seems a little suspect.
Very, actually. So I was just wondering.
Yeah, I'm pretty sure you have a bug in there somewhere.
Cool.
Cool.
Got the code too, but I don't know if you guys want to look at that. But
Not really.
hard.
What is? Does anybody have these? So can one of the TAs? Can you guys work this up?
Yeah, I can do that.
Okay. I think Kaylin did it. In fact.
Yeah, I have it. If you want to see it.
Are you at a place where you could show it?
Yeah. Let's see here. This is what I put.
What's the x-axis? Can you scroll down a little bit?
The x-axis. Are you asking about like what? I didn't label the x-axis if that's what you're asking.
But I mean, it was only supposed to go from 0 to 1.
Yeah, which is why I think I actually did the problem incorrectly because I think I misunderstood something. Well, I just went from 0 to XC, but I didn't know that XC was limited to 1. But I can change that real fast.
Okay, so this is for like a XC from like -6 to 6.
Exactly.
Okay, that's fine. Yeah, the problem though is that the error gets so big far away from 1 that it swamps out what's going on in the interval that we're interested in.
Yeah, so I can here. Let me go back and change that. You wanted to X 0.
Yeah, it should be 0 to 1.
That's not showing really much of anything. Let's see here. The range should automatically adjust, so I don't know why it's not.
It's because it's not Mathematica.
It's more reasonable.
I don't know if I can zoom in anymore. I got to figure that out later. But so like this is like here. See right here. This one's like the analytic integration error minus the approximate integration error. And since the approximate integration exactly replicates the analytic integration, we see that the error is like 0 across the
That's good.
right. And so this is just the analytic integration error. As you can see, drops off of the Taylor series. And then blue.
That's 1 point, and then yeah. Okay. So what are so the tilde is the analytic or the
approximate, I believe.
Yeah. So that makes sense. That seems reasonable. Yeah. So does anybody have questions on the trends there? You can kind of see. Where's the Taylor series one? Which ones are those? The bars or the tildes?
The analytic integration error is the E without anything on it, and then this is the analytic minus the approximate.
So
with
which
n
one
equals 2 points.
which one is sine of x minus the polynomial?
That's just the E.
Yeah, this is just
That's
the
the
E,
red
so
one.
that should be. It's gonna be
It's invisible.
Let's see here. I believe if I remember correctly, that actually I covered up like 6 to 6. Take this out real fast.
There should be some error, but it should be very small.
Yeah, if I remember correctly, like don't give me errors, don't give me errors.
Just out of curiosity, are you integrating these things in LaTeX somehow, Caleb?
No. So
Okay. All right.
So I just like, for example, for sine of x, I just did minus cosine of x and then plus 1 for the 0. For like the bottom, like, so that makes sense. The lower bound. And then I just kind of just computed the change of basis and then the quadrature rule. So I had like simplify everything down. And that's what I like, for example, this is what I plugged in.
Let's take a look at your plot again. Okay, so the E is covered up. It's so small.
I believe the red one is right here. I don't know. I need to figure out. I'll probably turn this in again because it sounds like I need to get the axes different. I need to figure something out because I'm not like a LaTeX guru. But let me see if I can open this up, make it better to see.
The PDF, you should just, there's that plus sign there in the bottom right.
So I'm still not seeing the red for some reason. Unless this is the red, but it looks more orange to me.
The scale, it's going to be small. You probably can't even, the line width might be bigger than the error, you know?
Yeah.
Yeah, it is. I just ran that problem, and the error is very small. It's there, but it's very small.
What's the order of magnitude?
It's like 10 to the negative 4th.
That sounds about right.
So you're never going to see it on a graph.
And that's the thing, guys. If you look at the truncation, if you were to look at that truncation, yeah, if you had like, I should write down, I'm going to add a section on Taylor series, but if you looked at the remainder, it should be on the order of 10 to the minus 4. So, Did you just write the code and run this problem in the time that we've been talking, Chris?
No. Yeah, I did.
Chris is a very bright guy. Okay. Yeah, and then the tildes were the difference between the
So that was the approximate integration error. So this would have been like the integral of sine of x minus the quadrature rule for sine,
yeah.
or the quadrature rule for the Taylor series, I guess.
Yeah, that looks really good because you can see that the blue line is the 1 point and it's not that great. Even though in the interval from 0 to 1, it looks so much like a linear function, it almost does an okay job.
Right.
And then 2 points, looks like it's better than 3 point. Interesting.
Yeah, I probably made a mathematical error there, so I probably need to go back and fix that. But I don't know. Maybe I'll just graph this up and not in LaTeX because the graphing is kind of janky.
You know, this is a nice problem because if you can work through the logic of this problem, this is what finite elements is, right? The basis functions that we're going to pick for our approximation space are kind of like the E. And then when we do quadrature, that's like the E tilde. And so the final solution that you really get, the error is really the E tilde is what we get in computed solutions. And so you can see here that E, you can't even hardly see it, but you can see what a dramatic impact that the numerical integration has.
So quick question on E, everyone's plotting the error and I see the error on my plot. However, when I integrate from E to C for that sine x minus sine hx dx, if I integrate from 0 to 1, I'm going to get an actual value. It's not going to be a series of values.
That's why you're ranging over C. So you integrate that integral a whole bunch of times to get a whole bunch of numbers. The integrand, if you look at the limits of integration, the upper bound is xc.
Right.
That xc is going to range from 0 to 1. So maybe you evaluated it like 0 to 0.1, and then 0 to 0.2, and then 0 to 0.3, and so on. And that'll give you 10 numbers.
Oh, okay. I see what we're doing there.
Yeah, it's a nice problem. Thanks for Kaylin actually helped. The first version of it, this is what I was trying to say, but it was totally wrong. And then Kaylin corrected me. So thanks, Kaylin, for that.
Anytime. So I do have a quick question, and it's almost like I guess I'm looking for some intuition on, because we developed all these mathematical formulations and everything. But and we kind of just dive deep into, okay, well, V is an infinite dimensional vector space. But I'm not entirely sure still what exactly problem we're trying to solve, if that makes sense. Maybe I'm just looking for, I don't know, for example, say if you took calculus 2 and you start talking about the amount of work required to pump water out of a tank, you kind of start with a picture and say, hey, here's how we're going to formulate the mathematical principles behind it. And I'm just not entirely sure how everything ties in, if that makes sense.
Yeah, we're getting there. The problem is that we can't even talk about that until you know some of this stuff. So the minimization, I can actually point out to you though, let's see. My screen here.
It's just like, I'm not entirely sure, like, we have a starting point, but I'm not entirely sure where our endpoint is supposed to be. I mean, obviously, solution to the problem, but I'm not really sure what the problem that we're trying to solve is.
So what is the problem we're trying to solve right now? Like we've only introduced one problem, and it's this one right here.
Okay.
So can somebody say in words what this is? What is the problem we're trying to find? What is the problem we're trying to solve? And maybe some practical applications of this idea. That's a good question, Kaylin, because this is like the beginning of everything we've done. So if you don't even know what this is, you have no idea what we're doing. So let's review what this is. How about this? How about this guy right here? What is this thing saying?
Well, if U is in like the finite dimensional space and F is not, then we're trying to find the closest approximation of F to U or U to F.
That's exactly what this is. That's this problem. It's basically, it's called least squares projection. Where is this used, by the way, besides everywhere? Give me some examples where this is.
Where least squares is used?
Yeah.
Is that what you're asking?
Yeah.
Well, I know it was used when they developed the new GPS system in 2010.
Okay. Yeah.
You use it when you're trying to compare maybe two plots to see how similar they are?
Yep. Maybe one where the people who are working at core form, where are we doing this right now? A lot. We're spending a lot of time on this actually.
Well, this is fitting to CAD.
Fitting to CAD. Yep. So in that case, F is a CAD model and U is some other spline object, and we're trying to get a good fit. Now, here's the point, guys. This norm, here we're using the L2 norm. Did you know, it's kind of amazing that there is a norm associated with linear elasticity, Navier-Stokes equations for fluid dynamics, electromagnetics, acoustics. There's actually an appropriate, what's called energy norm for those problems. And so they're all going to look like this. So like every physical phenomena that you've ever seen done on a computer starts out looking something like this with some appropriately selected norm, which is why I'm trying to get you to learn this stuff, because it is a ubiquitous abstraction. And if you master these tools, then you are like a Swiss Army knife, right? You can do almost anything. So the norm will come from the problem. And then, but the minimization idea holds irrespective of the norm. So if we have like, if we have a problem like linear elasticity, let's say, so if you need to go, you can. Why isn't this working? If we have linear elasticity and with appropriately selected boundary conditions, then what we're going to end up having is a norm. Let's call it the energy norm. That's going to look something like the square root of the integral 0 to L of, say, U, comma X, E, A, U, comma X. Okay, this actually, do you see this? This right here, guys, is, so this is just a bar, right? Being pulled by some force F. And then U comma X is nothing more than the strain. And EA U comma X, this is the stress. So strain, stress. Put 1/2 out here. So this guy right here is the energy of a bar in tension, where F now is an applied load. Okay, and this, so we're solving now for the displacement field U that minimizes the energy of the deformation associated with the associated deformation of the bars with respect to a given load. The thing that's really cool about what you're learning here is that mathematically, again, with appropriate, you have to have what are called Dirichlet boundary conditions, but so I've simplified it with boundary conditions a little bit, but this thing here actually is a norm. So that we can replace this norm with this norm, and all of a sudden we're solving an elasticity problem. So the point that I'm making here is that you guys probably are completely underestimating how powerful the tools are that you're learning here. And I hope you stay motivated to learn them, because there are these beautiful patterns that emerge that have been abstracted in the context of some of these mathematical ideas that allow you to understand a very broad swath of what we do in the computational sciences. So this is like elasticity in one dimension. This is the elongation of a bar. It's equivalent to a norm, the energy norm. And so once you understand it as a minimization in the context of a norm on an appropriate space, you have all the machinery of the Hilbert spaces to help you then just minimize it. So the next problem we'll solve is we'll go to this guy and we'll actually do it. And then I can draw some strict analogs between the math and something that you've seen before. So there is a certain, in these kind of advanced topics, you have to be patient. You don't always get all of the intuition at once. So we'll get there.
That does help though. Thank you.
Mm-hmm.
We are holding out hope.
You guys are funny. Give yourself like 5 years, not 5 days. Okay, let's stop there and appreciate the questions. So I guess I'll see you guys on Monday morning.
Thank you.